I'm Conor Hutton, and this is a talk I gave at Compila 2024. It's a recording. I gave the talk earlier in the week. Thanks to the organisers for inviting me. It was a fantastic workshop. I loved it. So, 2 points about language. 2 points about language we all know, but it sets the context for the talk. There are many important and interesting, fascinating things about language, but these are two of the most interesting and most fascinating. The first, of course, is that almost all children learn a language. This is, parents worry a lot about talking to their children, reading to them, enriching their vocabulary early on. The degree to which that's useful or affects long-term outcomes is very unclear, surprisingly unclear. It's very hard to disentangle the having the space and opportunity to read a lot to your children and other forms of privilege. The results are ambiguous, but what's not ambiguous is that children learn to speak, and this is true across different societies, different ways of organising the family. Just to choose one example of a very different culture, rich people in England, certainly in the 19th century, they cling to the traditions, so it's probably still a bit true now. They don't talk to their children very much. They send them away. They put them up in nurseries. The children still learn to speak. Here's the example of Thomas Babington Macaulay. Not endorsing him. He had terrible ideas about when he was involved in the administration of India. But his first words were claimed to be, "Are those the fires of hell I see burning there, Father?" He came out with this. Probably at that point he'd hardly ever spoken to his father. Children learn to speak. But, and this is the second striking fact, only children learn to speak. Maybe parrots talk to each other, maybe whales, but certainly our attempts to teach our closest relatives, the great apes, to speak have not been successful, not produced unambiguous results. It's clear that apes do have forms of communication. They gesture each other, they shout to each other, but these utterances don't constitute a language, and attempts to teach them a language have failed. Certainly, they haven't learned a language that was quite obviously a language, either based on gestures or utterances, and then use it to talk among themselves. Here's the tragic example of Donald Kellogg and Gua. They were raised together. Donald's parents thought that that would mean that Gua would learn to speak, but in fact, Donald learned to throw his feces at people who displeased him, and they ended the experiment. Only children learn languages. And so that's led to these two ideas. These ideas are at the center of our debate, our investigations, controversies in linguistics, controversies that spill out into broader discourse, into the broader culture. The first of these ideas is that languages have universal structures or properties, that the languages live in this low-dimensional manifold. There are a few things that need to be decided, a few switches that need to be switched. But once you've done that, once you've understood quickly as an infant what sort of language you're speaking, you still have to learn all the vocabulary, but you've understood the structure, how to make sentences, and so all your brain is doing then is grasping for vocabulary. That language lives in this low-dimensional space defined by these universal properties. So once one thing is decided, lots of other things follow. And then, implied in that is that humans are somehow born with an innate sense of what this low-dimensional space is, so that they can quickly grasp what sort of language they're speaking and learn to speak it. So these two ideas, like I say, they've dominated, they've clarified what we're trying to work out in linguistics. They were originally foregrounded by Chomsky a long time ago, in his review of Skinner's book, etc. And they have really made it clear what we're trying to do. Chomsky himself has sometimes taken, and certainly his followers have taken, quite an extreme view. This is this famous Chomsky quote. It's written down in New Horizons in the Study of Language and the Mind, but he uses some version of the quote quite often, used in talks and lectures and so on. And one of the things that first led me to work on linguistics was reading this. So he said, in their essential properties, even down to fine details, languages are cast to the same mold. The Martian scientists might reasonably conclude that there's a single human language with differences only at the margins. Now, that on first reading, on first hearing, sounds bizarre. Language is very hugely one from the other, and certainly naively, you might think that the things that they have in common are not things they have in common because they're human languages or their brain has some language instinct that molds languages in a particular earthling form, but rather that the things they have in common are necessary consequences of the properties of the world that they seek to describe, their use as a communication channel, the requirement that languages are reasonably easy to understand and reasonably easy to learn. I now, I guess, feel that there is more truth to this quote than originally, naively, I thought there was. But I still think it's kind of wrong. And one of the reasons I thought it was wrong from the start is, I'm very lucky in that I do have, from my schooling, some knowledge of Irish, Gaeilge, and Irish is a language which differs more from other Indo-European languages than most of them differ from each other. It has quite striking grammatical differences to English and French, the other languages that my first language and the other language I learned in school. Here are some examples. Tá saoirse uam, so saoirse means freedom. It's the origin of Saoirse Ronan's name, the actor Saoirse Ronan's name. And so Tá saoirse uam is I want freedom. Now, Irish certainly, the most common construction for expressing want doesn't involve a special want word. It uses a preposition, from, and Irish, as you see, has these compound prepositions which include a person. So uam means from me, uit means from you, uin would mean from us, for example. So, and then that's true of other egg means at. Agam means at me, agit means at you, aging means at us, etc. So that's one. Irish does a lot of work with these words, and so they do compound with the person. You can see also that the verb is at the start. In fact, Irish is a verb subject-object language, quite an unusual, certainly if you wait by speakers, quite an unusual form of word order. And so the construction here, is freedom from me, is quite different from the English, I want freedom. Here's another example. Tá lón uat is lunch from you, meaning you want lunch. And so that shows you just how much languages can vary one from the other. And these are actually both, English and Gaeilge are both Indo-European languages. Conversely, though, you are in a position already to make novel Irish sentences. So I come to this, I introduce this as an example of how different languages can be each from each, but at the same time you can see that there are universal properties of language that we don't really think of universal properties because they are so obviously properties that languages should have. The property here is the sort of the fact that the word saoirse will probably still mean freedom if you change the uam to an uit. So tá saoirse uit is freedom from you. You want freedom. I'm able to write that sentence because I know a bit of Gaeilge, but you'd have been able to deduce it or guess it from the examples above. And conversely, tá lón uam is lunch for me. I want lunch. Or give a more complicated example. If you knew tá lón uam, I want lunch. Ignore the red, which is wrong. And hunnig me an can. Can is the word for hound. It's also the origin of my name. So I saw me the hound. I saw the hound. And now you can probably guess at how you'd say I saw the lunch. Hunnig me an lón. And so, although Irish does teach you that languages can be very different from each other, it also shows you some of the properties that languages almost universally have. The fact that words have fixed meaning irrespective of context, the property that we refer to as compositionality. So, languages, when we marvel at the ability of children to learn languages quickly, we then conclude that there is a sort of language mechanism in the brain, and we think of that as encoding universal properties. There's another version of this which is kind of simpler, which is, that languages have properties that make them simple to learn, that we're already quite good at learning statistical regularities. We're quite good at connecting things, in this case connecting objects to words, and we have an ability which distinguishes a little bit from other animals of being able to sort of reason things out, to learn rules as well as to learn regularities, to learn explicit rules. And so maybe all that languages need to account for their learnability, to account for the fact that children can learn them, is children wanting to learn languages, a desire to learn language. That's a kind of an instinct, a language instinct, but not one that comes with a special language machinery. And an ability to learn and transfer rules. That's the ability, of course, that large language models are doing quite badly. They imitate it by learning efficient representations and learning statistical rules on those efficient representations, but that's quite a long process. That's what requires these vast corpora and this massive parallel learning. Maybe just because of the way that our brains have evolved to learn rules, we are able to learn these rules. In other words, maybe we just think more that languages have these reasonably straightforward and simple properties of this sort of compositionality that makes them easy to learn. That doesn't answer the second question, which is, or address the second idea, which is why only humans can speak. But that's something I'm going to come back to. And so this is the idea that we're interested in, that languages do have universal properties, but they're not the sort of universal properties that we, or they shouldn't be phrased in terms of the things like, the order of verb and object is matched to the order of noun and adjective. It's simpler properties around, compositionality, properties that are designed to fit into the existing cognitive mechanisms of humans that make them easy to learn. And so the two properties we're going to concentrate on, and here we're following in the pioneering footsteps of Simon Kirby and his co-workers in the early 2000s. They sort of clarified these as important properties and did work using the iterated learning model, which we're going to be talking about, to show how these properties can arise. So we're going to talk about expressivity and compositionality. And language is expressive in the sense that everything has a word. It's a sort of onto property. So orange and red are different colors, and so they have different names. To orange, there's the word orange, and to red, there's the word red. To everything, it's word. And of course, languages are imperfectly expressive. I think it's always quite striking if somebody asks you what colour your eyes are, you don't really know, because our colour words aren't very good at describing the colours of people's eyes. And similarly, when people say, what colour is the sky? You say, well, it's obviously blue, but it rarely, if ever, really is blue, and we don't have enough words to describe all the different colours of the sky. But expressivity is, to an extent, a property of language. And then the converse property is compositionality, that words describe just one thing or one action or one event, but they do it irrespective of context. So sodium lights on the street are encountered in quite different circumstances to orange robes that people wear, but we still use the same word orange for both. That the orange is a transferable signal that always refers to the same thing. Now, of course, again, languages are imperfectly compositional. We also use the same word for something quite different, which is the fruit orange. And we know that historically the word for orange comes from the fruit orange, and there's an interesting story there in that orange didn't always have a word for it. It was just somewhere in the range of red and yellow, and only at some point in our history did we feel the need to start having a word for the what we now regard as the separate colour orange. But that's all beyond the scope of what we're talking about today. What our idea is that languages, important properties of language are compositionality, expressivity, and then also if we're going to be doing agent-based modelling of of how these properties arise, and in the agents, we want there to be a property of stability as well. In other words, we're going to be modelling a tutor teaching a pupil to speak, and then the pupil then going on to become a tutor itself, and then teach another pupil. And we'd like the language to be fairly stable, so that parents can understand their teenagers. And of course, languages also change, and we can't always, or we're sometimes surprised by how our teenagers speak, or the use or the way they use words. But the third property we're interested in is some property, roughly, of stability. So these are three properties that we think languages have, and that we believe they have, to make them easy to understand. And what we're going to look at is a model in which these properties arise spontaneously. And this is a kind of a conceptual proof of the idea that there are properties languages need to have to make them easy to understand, but that these properties can arise in the language through the dynamics of how languages evolve because of how they are taught and learned. And again, this is due originally to Kirby and co-workers. So the iterated learning model. In the iterated learning model, we have a set of signals, which I'll call S, and a set of meanings, M, and then the agent that we're going to model, has a decoder, a way of mapping from signals to meanings. So you hear orange and you think of orange, and a way of mapping from meanings to signals. You see orange and you think the word orange. That's the encoder map. So we have a decoder map and an encoder map and a space of signals and meanings. But in this very simplified context, the spaces of signals and meanings are both spaces of n-bit vectors. And so the meanings are just, and here's, we do the example n equals 8. The meaning is just a sequence of 8 zeros and ones. So there are 2 to the 8 possible meanings. And the signals, again, it will be an n equals 8 vector, and so there are 2 to the 8 possible signals. So that's the plan. We have a set of meanings, a set of signals, and the language is basically the map from meanings to signals. It's how our meanings encoded in signals. And in this model, as I said, there's an agent. The agent has this decoder map and this encoder map. And the dynamics of the model is through a series of agent-to-agent interactions in which the language is taught to a tutor. So this is supposed to be taken midstream. The tutor is A5. It's teaching the language to the agent A6. And then the agent A6 is promoted to become a new tutor, and A6 teaches the language to a new agent, A7. And so this double line here is the promotion, the agent growing up, changing from a pupil to a tutor, and this B6 is supposed to represent the set of meanings or meaning signal pairs that the agent presents, the tutor agent presents to the pupil. And so at each generation, the tutor presents a set of meaning signal pairs to the agent, to the pupil. The idea is that the set of meanings is chosen randomly, and then the tutor will use its encoder to encode those meanings to signals, producing a set of meaning signal pairs. Those meaning signal pairs are presented to the pupil. The pupil will then, as I said, be promoted to an agent, and that pupil will then once again take a random set of meanings, encode them, present the pairs to the new pupil. And so in the particular case that we're looking at, the original iterated learning model, the decoder is a neural network. So as I said, the agent has a decoder and an encoder. The decoder is a neural network, and it's the decoder is a neural network, and it's the decoder that the pupil is training here. The encoder, the converse map, is a lookup table. So it's just a series of lookups. It says, that this meaning becomes this signal, etc. So the tutor is using its encoder, because the tutor is being presented with random meanings. It's using its encoder to work out the meaning signal pairs to teach the pupil. But the pupil, conversely, is training its decoder, which is the neural network part of this setup. So the tutor uses its encoder to provide examples. The pupil trains its decoder, and then at some point you have to go from the pupil's situation. The pupil has a trained decoder. It needs an encoder to become. The pupil has a trained. The pupil has a trained decoder. It needs an encoder to act as a tutor, and so it has to go from decoder to encoder, and that's done through a process called inversion, which is roughly speaking an inversion. So the pupil has a decoder. It inverts, or more technically, obverts that decoder to form the encoder. And so this double arrow here represents a sort of change in role. There's something fundamental. The pupil, when it's learning, is only learning to decode. It then has to change that into an encoding to learn to teach. So that's the setup. The pupil learns a decoder. It trades that in, as it were, for an encoder. It then becomes a tutor. It produces its own set of exemplars to teach a new agent. And then the reason that we call the set of exemplars a bottleneck is, of course, the tutor is only going to teach a subset of all possible of all the possible meaning signal pairs to the pupil. So the pupil will be training on a subset of the language, but it will have to it'll have to generalize that, because the set of meanings that it will use when teaching, when it becomes a tutor and has a pupil, the set it uses will be in general different to the set that it learned from. And so this setup, this iterated learning model, iterates across generations, but as it does so, it iterates between learning from a set, a subset of all possible meaning signal pairs, and then generalizing that to an other set of meaning signal pairs. And this works. So we have, again, this is me working with my co-workers Seth Bullock and Jack Bunyan. What we do here is just recreating the original results of Kirby et al. X, C, and S are measures of expressivity, compositionality, and stability. There's no real need to go through what those are. There's nothing super surprising. So expressivity is just some measure of the onto-ness, as it were, of the map. But they're the precise details are designed so that a completely unexpressive language or a randomly unexpressive language has x value 0s, and then a completely expressive language has x value 1, and the same thing is happening with compositionality and stability. And what you see is that very quickly in this iterated language model, the language evolves from generation to generation to have these desirable properties of expressivity, compositionality, and stability. The language settles down, and when by the time it's settled down, it's an expressive and compositional language. And so again, to reiterate, the idea of the iterated learning model is that there is a cycle of learning from examples and generalization, and in between the two there's this obversion. And so that's really nice, but of course it's obviously in a sense wrong, because this obversion isn't realistic in any way. So the problem with obversion is it's like you talk to your teenager, or talk to your child rather, or your child hears people talking. It sees things and then hears people naming them, so it's being presented with meaning signal pairs, but it never speaks, this child of yours, until about the age of 12, when like all children do, it retreats to its room. When your teenager retreats to your room, you don't really want to think what they're doing. But in this iterated learning model, what the teenager is doing is imagining it's doing the obversion. It's trading in its decoder, going from its decoder to an encoder. And as I said, that's a sort of inversion. So what it actually, in the mathematics of the iterated learning model, what it actually requires is that in this analogy, the teenager is imagining all possible meanings in the world. It assigns a probability in its decoder to the corresponding signal. So every meaning could be encoded in 2 to the n different ways, where n is the number of bits. It imagines the probability that this neural net would assign to each of those 2 to the 8 possible meanings. It then forms that vast 2 to the 8 by 2 to the 8 matrix, all meanings, all possible signals, and it does something that in a way, it produces a lookup table from that big matrix. And so it's computationally very expensive. In practice, this iterated learning model on without going to a heroic lengths, only really runs in reasonable time for n's up to about 12 or 14. Originally, the examples were all done for n equals to 8. But also, it's completely unrealistic. The whole point of language is that we can express meanings that we've never imagined before. In this model, at some point you have to make a transition from being a pupil to a tutor, and at that point you have to imagine all possible sentences, all of language, all possible meanings, everything that might ever happen to you. Maybe dreaming has something to do with imagining everything that can possibly happen to you, but it's certainly the obversion is not a realistic aspect of the iterated language model, nor is it a practical aspect. As I said, it presents computational challenges, and it means it sort of limits this paradigm to these pupil-tutor interactions. You can't learn and teach at the same time, and so it limits the application away from the sort of social interactions you might also want to model with it. And so we wanted to fix that, and the first idea, or the obvious thing to do, is just to kind of make the encoder and the decoder both into neural networks. And that's fine, except for in that case. And so you imagine that the tutor is presenting examples to the pupil uses the signal meaning pairs in both directions, one direction to train its decoder, one direction to train its encoder. The funny thing there, though, of course, is that the decoder is necessary as part of the mechanism of language comprehension and so on. But in literal sort of precise terms in this simulation, the decoder is not doing anything because it's the encoder that the tutor uses to teach. And so you've decoupled the two small networks, and then the encoder network, it kind of collapses. It starts mapping all meanings to the same signal, and that's a natural thing as you think about it. There's a sort of an everything is an elephant problem. If in the bottleneck set, the set of meanings that the pupil is being taught, it's been taught an elephant is called an elephant, so the meaning is something grey and large, and what it learns is that that's an elephant, and so in teaching, of course, it's a neural network. I should say the neural networks are very simple. They just have one hidden layer and all-to-all connectivity. In that neural network, it strengthens all the connections that map from bigness and greyness to elephantness, and so when it then comes to generalize, the neural network is incentivized to generalize, to strengthen those corrections, to have anything grey and big fall into the elephant basin. And so when it randomly chooses a large rock as a meaning, it will teach its pupil that that's also called an elephant. And so now we've lost some expressivity, and then that generalization, that growing of the meaning set of a given signal continues across generations, and in a very small number of generations in this version of the iterated learning model, everything is just, the expressivity is wholly lost. So that doesn't work. And so you have to find some way of coupling the encoder and the decoder. And we tried lots of different things, and sort of contrast learning and sort of a communication game aspect of that. And none of that was really working. And then we hit upon the idea of coupling the decoder and the encoder as an autoencoder. And so in this version of the iterated learning model, the agent has a decoder and an encoder, and it also has an autoencoder, which is made by putting the decoder after the encoder. And so the autoencoder is mapping meanings to meanings, and it's running through the same network. So here it is again. So here's on the left is the encoder. So this notation here includes a little bit of messing about the fact that at some point you have to integerize, so the neural network is producing probabilities, but you have to then map them to actual signals, which are bit strings. But basically the idea is that A is the encoder, B is the decoder, and then for the autoencoder, you overlap them. So you're using the same network, the same connections. You aren't adding any connections. But you're training it a different way, in the sense that you're putting in a meaning and you're taking out a meaning. And so here's the learning structure of this version of the iterated learning model. We have the tutor is teaching examples, it's providing meaning signal pairs. The agent is using that to train both its encoder and its decoder, but the agent is also, the pupil is also being provided with meanings, random meanings from the environment, another set, potentially the same size as the bottleneck set for the supervised learning, but it's learning these. It's learning these in an unsupervised way, because it's just going from meanings through the autoencoder and back to meanings. And so here we go again. It's a meaning autoencoder meaning training, as well as the individual trainings of the two individual neural networks. And so this works super well. I mean, in the paper, which is on arXiv, you can see millions of different varieties, but basically it learns the expressivity, the compositionality, the stability faster in lots of versions than the original version. It's super reliable, basically. And so this works. This allows us to get rid of a version. And the way it's working is, of course, that in the autoencoder set, if it's to be able to take a meaning and map it back to a meaning, it has to make sure that the signals have expressivity. So at some point, the meaning might be an elephant on a rock, in which case it's important that in its signal space it maintains a difference between elephants and rocks. And so, I mean, that's, I think, of practical use. You can run this very easily for much larger sets of meanings and signals than the original. you could think that that might allow you to study, for example, social learning or communities of speakers, the spreading of different languages and language encounters, etc. But you might also think that maybe you could do something more complicated, where you move away from these bit strings towards things that look more like languages, etc. So there's lots practically that you can do, but it also has an interesting implication for the nature of language learning. And of course, we're generalizing from a super simplified model that the map is not the territory, so you needn't take this too seriously. But this is what you might think. You might think that languages arise when utterances become part of thought, a tool for thought. So the idea you have here maybe is that in very simple animals, they go from stimulus to action. You watch a spider on the ceiling, and the light comes on, and it moves towards the dark. There's a direct kind of stimulus action map. But for more complicated animals, there's a thought process in between. When they make these decisions, it's not simply a trivially predictable consequence of the stimulus. You look at the way that hamsters behave or whatever. It may involve some sort of learning. Obviously, there's a little bit of this in spiders. You can condition a spider, you can condition a fruit fly, but as you move towards more and more complex animals, there's more and more thought involved. There's a stage between the stimulus and the action. And then you have social animals, and social animals have utterances. So, I have chickens, and the chickens, if a hawk flies overhead, they shout to each other. So they are making utterances because part of what they want to do is to promote the well-being of their community, or involve themselves in the dynamics of the community. They shout at each other to assert dominance, etc., or to request help or something. So there are utterances in these social animals, and they are the output of the thought. But of course these are just utterances. Birds. There's only 7 things that birds say, and for a given type of bird, it's always the same mapping from those 7 things to those 7 utterances. And those utterances are like gestures. They're not part of thought. They don't think in these utterances. They don't play an internal role, the utterances. They are an output of the thought. And so the idea might be that at some stage humans started internalizing these utterances, that they had the cries that they made, but by imagining themselves making those cries, it helped them particularize their thoughts. It helped in these hominids that are preceding humans. The utterances become part of thought. The imagining of a potential utterance becomes a mechanism for particularizing, directing cognition. And at that point, the humans are starting to behave like an autoencoder. That's the idea, that at some point in our history, we internalized our utterances, and that promoted the unfolding of language, because it allowed language, or forced language towards this expressivity, that it was a tool that moved utterances towards linguistic systems. And so this is the idea, that languages have universal structures of property, but those structures of properties are slotted in to the existing cognitive machinery of human thought, as it were, or of hominid thought. And that's the first thing. That secondly, the simple change that allowed humans to be programmed for thought, that distinguishes humans, programmed for language. The thing that distinguishes humans and makes language learning this unique property of humans is just the internalization of our language to make it part of our cognitive process. And when that happens, we become so much better at learning language and using language, and the languages that we develop around our communication and thought processes become so much richer that we have the human language facility. So that's what I wanted to say. Again,